Hello, so welcome back to our channel. And this time we have brought to you a circuit as shown on your screen. In our previous model, we talked about how to design an analog integrated circuit using a spice simulator. And in that, we demonstrated and understood the performance of the and the behavior of that particular circuit using 180 nanometer technology process. So that's the model we used to predict the behavior of this circuit and the operation of the circuit. Now, this time, this model focuses on showing the performance or the behavior of a single transistor, which we picked up from the device library of this SPICE circuit simulator. And we will simulate its IV characteristics, that is current versus voltage. And in particular, we would show the effect of the voltage that we can apply on the body of this transistor. So as you can see, there are four pins to this transistor. This is a drain pin, this is a gate pin, this is a source pin, and there is a four explicit connection to this node, or that is called as the body of the device. So in case of NMOS, the body of the NMOS is P-type substrate. So we will say it has a P-type body. If it is a PMOS transistor, then it has N-type body or N-type substrate. So what I did is, as you can see, this transistor I picked up from the device library right here. I clicked here and then I typed NMOS. So there are two types of transistor I had, NMOS and NMOS 4. So I chose NMOS 4 because this is an N-channel MOSFET with explicit substrate connection, which is used in the case of single crystal silicon, which is used to fabricate the integrated circuit. But there is another MOSFET with the name NMOS, which is simply says it is an N-channel MOSFET, and this body is already tied to the pin that is the source. Okay. So alternately, their counterparts will be named as PMOS and the PMOS 4. Okay. So we will see the behavior of NMOS 4 and the PMOS 4 in this module. So what I did is, okay, you can see that once you choose a transistor and select OK, then this transistor is available to be placed on the schematic. So I will press escape button on the keypad to get rid of it. And now I will focus on the NMOS. So to the drain pin, I have got the voltage here, that is VDD. So I am applying the VDD of 1.8 volt to this node. So how I will ensure that this voltage 1.8 reaches here. So I can show you, I will right click here and I will click highlight net. So it means I have labeled this net as named as VDD, and here also I have labeled this name, labeled this net as VDD. Okay. So how I did it? I just right click this net and I click label net. And then with that option, I said VDD. And I said, okay, it is an input type of port. Okay. And then, or maybe this is not an input type of port. I just kept it none. And then I clicked OK. And then I placed it right over here. And I placed it right over here. Similarly, same action I did for labeling the nets at this node and at this node, at this node, and at this node. So you can see this label net is labeled as VB. Here, this net is labeled as VB. And you can see that this is the connection to the body of the device. So that's the voltage applied on the body of a device. That's the voltage applied on the gate of the device. Okay. So how to label this net and then choose it as a whether that's the input or output. So you can select from here. Okay. So for example, if you choose input, the symbol comes like this. If you choose an output, the symbol comes like it. So that's not the focus of this model to explain you about how we can make the circuit connection, how we pick up the library components from the device library. We have covered all these aspects of using how to aspects of using circuit simulators in our previous modules in the playlist. You can always go and refer to those. So the focus here is to predict the and understand the behavior of this device, especially its IV characteristics. Okay. So like I said, it has got four pins: drain, gate, source, and the fourth one is the body. And on each of these four pins, I have applied the voltages. Those voltages are VDD of 1.8 volt, VG of 0.75 volt, ground is connected to the source is connected to the ground. And on the body, I initially have used the voltage 0. So it means this volt net, that is the net of the body, is essentially connected to the source as of now. Having said that, what we can do is now the question is why I applied 1.8 volt and why I applied 0.75 volt. So assuming that it is an NMOS transistor, I right click here. After right click, I get the properties of this monolithic MOSFET, which reads me, okay, this is a model name is NMOS. That says it is an NMOS transistor. Then I have to put the parameters L and W and drain area and source area and drain perimeters and source perimeters. And I have to say how many numbers of devices are there to be connected in parallel. Okay. So if I don't mention the drain area, source area, perimeters of drain and source, and the number of parallel devices, when I will simulate this circuit, the SPICE circuit simulator internally will take the default values of these parameters from the SPICE deck or SPICE card that this simulator will use in performing the simulation. I repeat again, it will use the default SPICE card if I don't mention these parameters. Okay. And if I mention, then all these given parameters will override the default values of the parameters. Now, where are the default values of all these parameters if I don't want to specify anything? So what you can do here, we are using the level 1 of the MOSFET because we are not defined the level of this model for which we are using, and we are going to simulate for that model. So what I'm going to show you here, you can click view. We will have a look at its SPICE netlist. Once your interconnections are done, circuit is ready. And before that, I forgot to tell you what analysis we are doing. So we can do the first analysis, which is the .op analysis. For example, .op analysis is defined by .op. So let's say here, and then there is a .dc analysis. So let me explain you one by one. So .op will give us the operating points of the circuit once you run the simulation. It will show you voltages and the currents at the given operating point. The way you have put up the voltages on the all four pins, accordingly the currents and voltages of this transistor will be calculated and will be displayed. Next analysis we will perform is the DC sweep to obtain the IV behavior of this MOSFET. Okay, and the third advanced analysis we will do later. We will also sweep the voltage at the base or the body, and then we'll see how the IV characteristics looks like. Okay, so the first thing first. For example, if I choose .op and .dc, how is .dc defined here? We have also covered the separate model, but I will briefly explain you. I right click here and show you how I defined it. So I use the edit simulation command, which I can go from simulate from here also. And then I chose the DC sweep. Okay. So it is going to compute me the DC operating point of the circuit again while stepping independent sources. And meanwhile, it will treat the capacitances as open circuit and inductances as short circuit. So what I do, I clicked on the first source. Then I said, okay, V1 is this source. Use the linear sweep. Sweep it from start value of 0 volts to 1.8 volt, which is the final value, and then at the increment of 0.1. So the command was .dc V1 0 1.8 0.1. It was my command. But then I click the second source here, and then I said, okay, sweep V2. So name of the second source V2. Use the linear sweep. Sweep V2 from 0 1 to 1.8 at the increment of 0.1. So I got V2 here, V2, 0, 1.8 and 0.1. Okay. So once that is done, here is the syntax. You can see that how this syntax is defined. But for GUI, graphical interface, it's easy. Just use. So this kind of sweep is called as nested sweep because the IV characteristics will be between IDS versus VDS at various values of VGS, right? Or simply say it's the ID versus VD with for various values of VG. Okay. So, I assume that you already know the output characteristics of your transistor. We can also have the input characteristics of the transistor, which is ID versus VG. So you can simply keep the VDS fixed and then sweep VG and obtain the value of ID. Okay, so we'll do that later, but that is all there. Now, I will click view and I will show you the spice netlist. Click the spice netlist. Look at this, what I explained here. It shows us that's the library in which the circuit is stored. The name of the circuit is exploring the body effect in CMOS transistor using spice. Now I have got V1 that is connected between VDD and 0. So VDD and 0, 0 is the ground net and its value is 1.8. So I'm teaching you how to read the spice netlist. Then I have V2 that is connected between VG and 0. So here is V2. Net level is connected between VG and 0. Value is 0.75. Then I've got V3, which is VB connected between VB and 0, and it has value of 0 volts. So here it is, our voltage VB source VB is this one right there. Now next, then came here the transistor labeled as M2 right here. So here is M2. It is connected between VDD, VG, 0, VB. Now, how did it come? Just remember the spice voltage earlier. I haven't really shared with you this particular window right here. Okay, so let me share with you that. So here we actually have defined the syntax of the spice. So as you can see that the monolithic MOSFET, how it is defined in the spice, that is MXXS, ND, NG, NS, NB, and then its model name M and L, then width, then the drain area, source area, etc. Then example is M1 is defined connected between drain connected at node, gate connected at node, source connected at node, and the body connected to the 0. And the name of the model is my MOSFET. Then we define dot model, my MOSFET, and MOS, KP equal to 0.001. So here my MOSFET is a model name. NMOS is the type of the device. So it is NMOS, then NMOS. For a PMOS, example is M1, drain is connected to node N, gate is connected to node N, source is connected to node S, base body is connected to node N, and then name of the model is P MOSFET, my P MOSFET. And here then syntax is dot model, my P MOSFET, PMOS, and KP equal to 0.001. Okay. And then I explained you about this there are 7 monolithic MOSFET device models. Okay. So the model parameter level specifies which model we are using in the circuit. If you don't specify the level, then the default is level 1, which is Schumann Hodges. So in the earlier discussion, I have explained you all these parameters also. I gave you definition, but the screen wasn't on that time. So please refer back to those discussion and link it to this screen. Okay. So coming back to our circuit here. So here M2 is connected between drain is connected to the VDD. You can see the gate is connected to VG. The source is connected to 0 potential and the body is connected to node VB right over here. And the name of the model is NMOS. And then comes the dot syntax here. Dot model NMOS, NMOS, dot model PMOS, PMOS. Now, we haven't used the PMOS transistor on the schematic. You can see that. But still, by default, the spice is writing that syntax for the PMOS as well. Okay, but we have only one transistor defined in the netlist, which is M2, which is NMOS. Then comes the library. So you can see that it is using the standard MOS model of the from the library, because here in the dot model card we can define here and write. If we here we cannot write, but if we don't draw the schematic and choose the describe the behavior of the schematic by using the netlist, then you can use the word pad or notepad and start writing the such syntax. Okay, so it's a kind of another approach of creating the schematic. So here you can see that we when we write it instead of drawing a schematic, then we can define on this dot model NMOS and MOS. After that, we can write level equal to 1, 2, 3. So now there is no level defined. So default that the circuit simulator will use is level 1. Then dot .op is our operating point analysis. Dot .dc is our DC sweep. Back annotation, it means it will print the voltages after the simulation is done, and it can be highlighted on the schematic by clicking the nets, and dot end will end the spikes deck. So close it and we are all set. So now we are using the level 1 MOSFET model by default because we haven't defined any model. Okay, so what we'll do is disable this analysis initially. We'll just run the open operating point analysis. So let me do that. So for that, I will just do like this and I will run the simulation now. So you can see here, I have got VDD equal to 1.8 volts. So this is the voltage at different net or different nodes. VG equal to 0.75, VB is 0. The drain current flowing in the MOSFET is 5.6 micron. So that's the current is with the given voltage on the gate and all that. The voltage at the gate is 0. Sorry, the current in the gate is 0. Obviously, it's the metal oxide insulator. There is no gate current. And the body current is negligible, is minus 1.81 picoamp. So that's the current through the P-type substrate to the MOSFET. IS is the just opposite in magnitude. That is minus 5.65. And that's the current from the source V1. And so that's a simple calculation. Now, you can see that there is a drain current flowing. The gate voltage is there. And we got the value of the drain current, about 5.6 microampere. And we haven't defined the model. Now we are going to perform the DC sweep. So we'll click here and enable this analysis. And dot op we don't need because DC sweep will do that automatically. We'll disable it. So now we are done, and now we'll click here, run. You can see there I have another spice netlist that I will describe you later. So here, as you can see, if I choose not to draw the schematic, but rather open the schematic window and just copy paste the code or the netlist I have created using Notepad and paste it on the screen here. So this is how I will define. So M1 is there, drain is connected to node 2, gate is connected to node 1, body and the source are connected to node 0, that is ground voltage, and the name of the model is NBSIM. Then I use the VGS, which is connected between node 1 and 0, and its value is 3.5 volt. Then I use another voltage source called VDS. It's connected between node 2 and 0. Its value is 3.5 volt. Then I'm going to use the DC sweep analysis. I'm using same command like here. So it is sweeping VDS voltage source from 3.5 to 0 at the steps of minus 0.05. And in the same sweep, which is called as nested sweep, I'm sweeping VGS from 0 to 3.5 at the intervals of steps of 0.5. Then comes here the dot model. The name of the model is NBSIM. The type of the model is NMOS. I have explicitly mentioning the level to be used. It's a quite advanced level, so more accurate modeling will give me a result. And finally, I'm then saying, okay, uh, once that is done, save the current, which is the I as a function of VDS, and it will plot when with this command, it will plot me on the screen the current. So we'll do that later, but for now, let me minimize it and we'll just have these two windows here. So after running the simulation of this schematic, we've got the screen open. Now what we want to do is I want to plot the current, drain current. So I will hover the mouse on the schematic. So when the red probe is there, that's asking me to plot the voltage. But if I take it down, you see it is the appearance has changed. So if you see the extreme bottom left, there is some prompt, left click to plot ID of M2. So I will right click to edit. It says left click to plot ID of M2. So I will click and it has plot me this current, that is the drain current of M2, which you can see that for various values of VGS, it plotted me those values. So I will just see that. You see now for the level 1 model, which is the very basic model of the MOSFET, the maximum current is 33 microamp. When I sweep the VDS from 0 to 1.8, the current is from 0 to 33 microamp. And these are the values of VGS from 0, then 0.1, 2 up to 1.8 volt. How about you use a specific model uh, into the into this same device, and we'll see how the characteristics look like. So what I will do is I have created this Spice netlist. So I will click view Spice netlist, and then I will just select all, right click. No, it doesn't do that. Oh, it gives me option edit as independent netlist. So here is that netlist right here. So for example, let me store it somewhere. For example, let's say I store it on desktop. So it is .netlist files and I save. Here it is, right? So it got me there. So now if we can write here level equal to 14, and we'll see what are the what parameters or what level 14 is. So here you can see that the level 14 uh, would be right here. It is BSIM 4.6.1 from University of California, Berkeley. It's a quite advanced model, right? But nowadays you have level 43 and all that, and that's the latest one. So we are using level 14 for our circuit. We'll see how the characteristics will look like. Can we simulate this now? Run. Numerical value expected here. Evil. Is there some mistake or something? We have to find out syntax or something like that. So click the draft here level. Maybe we have to be okay with these simulation and all this. So we'll do one thing coming back here. So maybe let's say if we do that and then let's say, okay, run. Ah, maybe here. No, it's not working out here, right? So there is some problem between them. What about level 1? No, but how come we got on this draft, We can see that, right? So how about we just copy this, maybe right click. That's in fact the spice directive. Okay, we can do that, no problem. So let's say here and copy paste that, and maybe from here we just close and well, that's the problem. We don't need to write it level 14 on M2 line. We have to write it here for the dot model level 14. Okay, so that's wrong. Oh, so here is you have to be careful actually. We don't need this, right? And this in okay, so level 14, we haven't used PMOS, but still we'll add it to PMOS also. Once that is done, now click run. Good. So we have got you see this graph, earlier graph. This is our earlier graph for level 1 model. Now we have simulated for level 14. So let us do that. So where is the graph? Right here. And we missed one line. We actually missed one line. It means we actually have to also give this command, that is save .vds. So we'll just right click and then copy and then go to our cancel and then go to our spice net list, right? And here is what it is. We can actually also do that, right? So save it, run it. Look here. Now select the waveforms, it says. So let's say I of M2. Are we doing it while I of M2? No, here. So let's say right click, zoom fit, add trace maybe. Here, ID of M2. Now look at this graph. Uh, if there are some changes, you see I of MT, is that the same graph? Yeah, there is change. Look at this green line here. It's a kind of a ramp here, but look at this graph is much better maybe. Yeah, if you look at the two graphs, there are changes. Now, I will show you how to simulate, let's say, the ID VG characteristics. So what we'll do is VB, we'll sweep the VB. Okay, right here. So let me do that. Where is that? VB is there. But before that, we'll just see we are increasing the VG and we are plotting that. So let's say I use the this is the command V2, right? So we'll just disable this analysis for a moment. That is disabled. And now I want to sweep VG and keep all voltages constants and then plot ID. So I will just go to simulate, edit simulation command, here DC sweep. So the first source is V2. That's the source I want, actually linear. And second source here. In fact, I don't want that because I'm not using nested sweep. I just want ID versus VG. So let's do that. So here, I'm sweeping this second voltage source V2, which is the voltage at the gate. So and we'll see the behavior. So let's go. Now let's close this. Draft also we don't want. So here is the plot, and let's go to plot the current. Here is that. So you see now there is the threshold voltage is about 100 millivolt or something like that, 120 millivolt, 100 to 120 millivolt. But by default, the model says if you don't specify the level, then the model will use the level 1, which has zero threshold voltage, like we discussed. But here it shows the threshold. So that's the thing we want to understand. What about now uh, using this spice deck? So for example, open, go to desktop where we have saved our file, netlist, this file, exploring this one. And here is our deck. And let's go for level 14, what we have done, level 14. And let's sweep only the second voltage source. So we'll disable this command. Okay, and we will enable the new command, which we want. So here is that command. .dc sweep V2 from 0 to 1.8 volt at the step of 0.1 and save I of VDS. So we'll see how it behaves. So right click run, and it says there were no valid node or device currents found in .save command. So please pick the data you wish to save from this simulation. So we'll want this one, I of M2 here. So we'll right click here, add trace ID of M2. We'll see if there is some change or not. Is there some change between the two characteristics? Yes, the current here is 33 microampere for 0 to 1.8 volt. The current here is about 500 microampere when you sweep it from 0 to 1.8 volt. So there is a difference between which current, which model you are using, right? So this model is for the short channel model because the level 14 short channel transistor. This is for the long channel transistor. Okay, so if you zoom in this level, so it's about 150 millivolt. The current starts increasing. Here is about 320 millivolts, right? About 280 to 320. So that's all about your stuff, right? How about you do the ID nested sweep? So first source, let's say V1, then linear 0 to 1.821, and then second source, let's say V2, 0 to 1.8 to 0.1. Click OK. So here we are done. Now we are going to run the DC sweep. So let's right click run and look at this characteristics. You got ID versus VDS for various values of VGS. How about spice take? We will disable this command. We will enable this command. Same, but level 14 here. Here is the level 1. Here is the level 1. Now here is the level 14. So we'll click run. Again, it says that, okay, you don't have to space I of M2. And look at this. You can see the difference between the values of the current. So here you have the currents about 0 to 33 micron like this. And here you have more flatter version, but here you have longer rise and then little bit saturation. But here your transistor is saturating about 1.2 volt. Okay, here your transistor is saturating at about 1.6 volt, close to 1.6 volt. So that's the difference. So I think you are doing good here. We are doing good. Now we'll see the body effect. So what we'll do is for the level 1, come back and just a moment. Okay, so far so good. So what we are doing here is let's now keep the VD fix and then do VG and VB as a sweep, right? So we can see that how the input characteristics, that is ID versus VG, for varying voltage of VB will change. Okay, for the level 1 model, and then here for the level 14 model. So this is a this is a long channel transistor. This is a short channel transistor. So we'll come back here, and here right click on this command. First source is our VG now. So it is V2, which is okay, 0 to 1.8 volt. But the second source is not V2, rather it is V3. So that's how you got the command change now. Once that is done, right click, click run, and here you have to see that now. Do you have any change in the characteristics right here? Oh, you don't really have any variations here. Seem to fit because you are sweeping like VG, and then you are sweeping VB also. Okay, so there is something to be understood here. V3 is okay. How about we change it to, let's say, 0 to minus 1.8, then minus this one. We'll see that if there is some change. Run. Not really, not really. So this is not the way we will do it. So what we have to understand here, let me see. Okay, so you can see that what I am doing here, I am sweeping the voltage on the gate, that is voltage source V2 and then voltage source V3. So it is giving me ID versus VG for various values of VB. But I don't see any difference for the long channel transistor where I have used the level 1 model. Okay, even though I have performed this nested sweep. However, when I do the same sweep in this kind of short channel effect transistor where I have used the model level of 14, I am sweeping the VG for various values of VB. You can see now I have got and obtained such characteristics, which is again ID versus uh, VG for various values of VBs here. So let me zoom in and show you how this is working. So you actually can see that I have varying threshold voltages for different body voltages. Okay, so here is like if I right click here and then say view and then maybe select state. So for example, V3 is 0. So it means I have this green curve. The threshold voltage here is about 100 millivolt. If I go to view, select step, and then I go to 0.1 for a body effect. So I have got this one. So again, view, select steps, and let's say 0.3, 0.6. So you see that this is different threshold voltages are changing here. And then there is this drain currents also changing. So this is how we can simulate the body effect in the transistor actually. So zoom fit, again, view, select steps, and we'll say that select all, and we'll see that. So here you can see, here you can zoom in, maybe you can see that there is a variations. So a lot of things are happening. So that's how that was about using the body effect and understand the behavior. You can use any 180 nanometer technology file and include it in the library uh, of the spice deck and simulate whether netlist or schematic and you see the performance. Hope you found this video useful. If you did so, like, share with others, and thanks for watching.